All right. All right. Happy Tuesday, Tuesday, week 9. Crazy. We are so close to done. Today's the last of the new material, and we're going to learn about hypothesis testing. On Thursday, we learned about how to set up a hypothesis. Today, we're going to talk about what it looks like. Look at like the conclusions, like what the testing of the hypothesis looks like, and then we're going to look at the math for population proportion and testing our hypothesis about the mean. So we're going to be using confidence intervals again, and we're going to be using them a little bit different, and we're going to be doing some comparison. So Section 10.2, after we talk about the different way a conclusion can look on hypothesis testing, then we're going to talk about how we test hypothesis about the population proportion. This goes with 9.2 and it goes really well with 8.1. Okay, nope, 8.2. 9.1, 8.2. I don't know what I'm doing. I do know, but Anyway, doesn't matter. Doesn't matter which sections they are. So we're going to do proportions first, and then 10.3, we're going to talk about hypothesis testing about the mean. So that is tonight. And once we're done with that, you know everything you need to know. And remember, we do not have class this Thursday. And then next Tuesday, I will have drop-in office hours for the test that opens next week. So next week, week 10, we have is the test and obviously finishing up the homework and everything, but there won't be any new material. We will have class on Tuesday. We will not have class on Thursday. Tuesday will be the last Zoom meeting. Then week 11 is when your final project is due. So I want to remind you, the presentation and the paper and the written report are due on Tuesday of week 11. So 2 weeks from today is the presentation and the paper. The presentation, you are just uploading it to the discussion forum for the final project presentation. You will post it there and you will need to leave comments, meaningful comments on 3 of your classmates' presentations. More is better because this is a very large class. I do not expect you to leave 60 comments because there's 60 something students in this class. I do not expect you to leave 60 comments. But more than 3 is probably would, people appreciate your comments, but 3 is what you get points for. You're going to get 3 points per meaningful comment up to 3 comments. So minimum of 3 comments you're required to do. And even though the forum doesn't close until Thursday, I will not give you a grade for any presentations posted after 11:59 p.m. that Tuesday. It won't let me just close new posts and not close replies. So I have to keep it open. But the presentation is due Tuesday. The paper, the written report, that is also due Tuesday by 11:59 p.m. Remember that you cannot pass the class if you don't turn in both a presentation and a written report. Those are required to pass the class. I don't make the rules, but the final, you have to turn in a final in order to pass the class. But you can do it. You've got this. All right. Now that the housekeeping's out of the way, let's jump into hypothesis testing. And that's hard to say. All right. So let's talk about, we already talked about how to set them up. We're going to talk about how to decide whether you reject the null hypothesis or fail to reject the null hypothesis. What kind of numbers are we looking for in the end to reject or to fail to reject? So we have a random sample of 1,000 people that say they are, and 534 of them said that they are in favor of banning cell phone use while driving. So that's 53.4%. So what we're looking at here, is it possible that could the true proportion be less than 50%? Or, do we just happen to have a survey that has more people than 50%? agreeing that they should ban cell phone use? Would it be unusual if it was actually 50%, if it was actually 50% of the people that were in favor of banning cell phones, would it be unusual to get a proportion that was 53.4% or higher? We need to know whether or not this is statistically significant, whether or not this would be unusual. And I know that up until now, 5% has been our rule. 2 standard deviations away has been our rule. And a lot of times it still will be. But remember that alpha that we talked about? We talked about this with our confidence interval, where sometimes our alpha was sometimes we had 99% confidence intervals. Therefore, the difference, there was only 1% outside of that 99%. So we were more than 2 standard deviations away on our confidence interval. Sometimes with hypothesis testing, it's the same thing. If we are using an alpha, which is that 100% minus our confidence level, if we're using an alpha smaller than 5%, then that's the number we're going to be looking at. You'll see as we get going. All right. So we say something is statistically significant if it is unlikely to be true, if our null hypothesis is not likely to be true based on getting that sample. So if I get a result like 53.4% rather than 50%, and it's determined that the probability of getting that result is too small for my hypothesis of 50% to be true, then we say it's statistically significant and we reject the null hypothesis. I'm going to get to some specific with numbers in a minute. Now, I'm not going to require you to use the word statistically significant. It's just something you're going to see. As long as you communicate well to me what's going on, I'm going to take it. I want to know when you are giving your conclusions, I want to know why you made that conclusion, and I'll talk about what that looks like. There's going to be 2 hypothesis tests on the test next week, one for proportions and one for means. You are going to have to do every single piece in your work, start to finish. I'm going to show you exactly what I want that to look like. So there's no question on, am I doing enough? Is this not enough? I'm going to show you start to finish everything that I want you to show in your work. I'm not here for surprises. I want you to be able to do it start to finish and have every little piece in there. All right. So to determine if our 53.4% is statistically significant, we have to build a probability model. So first we need to see if NP times 1 minus P is greater than or equal to 10. That helps us to determine if our sampling distribution is normal. This allows us to determine whether or not we can use this. So, and then also we have to test, is our sample less than 5% of the population? That's what shows us independence. Okay, so we've got all that. We're normal, we're independent. Our mean is going to be the population proportion. So in this case, our mean is going to be whatever we're using for our null hypothesis. So in this case, our null hypothesis, or what we're believing is true until we prove otherwise, is going to be this 50% right there. That's what we're going to use for our new standard deviation. We've done this before. This is not new stuff. We did this with our confidence intervals. So this would be my new standard deviation, and it is nice and lovely and whatever. So there we go. All right. So this is just the drawing. This shows 1 standard deviation away from the mean. It shows my nice bell shape. It is nice and pretty. This is just a drawing. Okay. So because we're not getting in the nitty-gritty of the math yet, we're just going to use a z-score of 2. We're just going to say, now that we have our new standard deviation, is my sample within 2 standard deviations of the mean? That's going to be the number we're using right now. We're going to be using critical values like we did in confidence intervals, but we're not there yet. So just give me a minute. So let's say we're going to use 2. 2 is that critical value. So we're going to check Is my sample more than 2 standard deviations away from the mean? 2 standard deviations are our sample size, our sample right here, based on the mean and the standard deviation that we just calculated, has a z-score of 2.15. That z-score of 2.15 is higher than the z-score of 2, which would be 2 standard deviations away from the mean. So since that z-score is farther away than the edge of my confidence interval, we would reject the null hypothesis. So if the z-score for my sample is farther away than the critical value, which is based on my confidence level, my confidence interval, then we would reject the null hypothesis. This is one method, one of our methods. We're going to get into we will be doing the math and it'll become even more clear then. All right. So the other way that we do this, and we're going to show you in just a minute, the other way that we do this is going to be using probabilities. So right here, this shows that there's 0.0228% to the right of my 2z score. I'm not sure why we're there yet. All right, this is why we're there. All right, so in the tail, 2 standard deviations away, it's slightly more than, slightly less than 2.5. Because remember when we're 95%, about 95% is in here. It's not exactly 95%. Remember for our um, empirical rule, it was an estimate. It is slightly more than 95% in the middle when we use 2 standard deviations. So what it really puts us at is that 2.28% in the tail. So now if I can calculate the probability of getting a sample with this with the 53.4 0 point. So if I calculate the probability of getting this or getting a z-score of 2.15 when my mean is 0.5, and that probability is smaller than this, smaller than the area of that tail, so it lands me maybe out here, then that's also going to be rejecting the null. Give me a second and I will make it a little bit clearer. Okay. So let's jump into the p-value. P-value is just probability. Whoops. They call it a p-value, but it just means probability. So our other way of doing this, we determine what is the probability of getting this proportion if the actual proportion is 50%. So what is the probability of getting that proportion if the actual proportion is 50%? Let me show you what that looks like. Okay. So I'm going to look for the probability of getting that or higher. So we already determined that the probability of getting, so the area of this tail right here was 0.228. Let me go show you. So what I do is I take this z-score right here. This z-score right here is 2.15. The probability of getting that z-score is this right here. That probability is smaller than the probability of being 2 standard deviations away. Because that is smaller, we reject the null hypothesis. So obviously looking at the z-scores, it's easy to see, but we can use this to bypass z-scores. So we won't need z-scores at all because we're going to get something called a significance level, and they will give us the significance level. So if our significance level, which is alpha, so my significance level, if it was 0.025, so 2.5%, which is approximately what's in that, and I get a p-value of this, if p-value is less than alpha, We reject the null hypothesis. Reject the null hypothesis. This is the second way to calculate this. Once we're actually doing this with examples, it's going to be a lot easier to understand. It's really not that complicated. It just sounds like it because we're not doing it with an example yet. So don't worry. Okay. All right. So let's actually jump into the math. First, I want you to remember what a p-hat is. To calculate the p-hat, you take the number of people with a certain number of individuals with a certain characteristic and divide it by the sample size. Just a reminder, we've been doing this for a while. Just want to remind you. Okay. Also to recall, these are the things that we need. These are the things that we need to test before we can do any of our math. That was weird. Let me get rid of that. These are the things that we need to test before we can do any of our math. So we need our simple random sample. You can state that you're assuming it's simple, that it's simple random sample. Assuming random sample is fine because a lot of times it won't say. NP times 1 minus P greater than or equal to 10. This tells us that our sampling distribution is normal. Then independent of each other, this is the, my sample size is less than 5% of my, that's of the population. These are the three things you will test on a proportion before you start doing your math. Test these three things. When you are taking your test next week, test these three things first. Show me you've tested these three things. This right here is our new standard deviation. That's the new standard deviation. We've been using it for a couple of chapters. And our mean is whatever proportion we're using for our null hypothesis. All right, so these are our necessaries. Okay. Now, reminder from previously. A two-tailed test is when you see, when we use not equal to, you see words like different. The word different. Left-tailed test is when we use less, the less than symbol. So you might see less than has decreased, etc. This we kind of talked about this on Thursday, but it's been a little while. So right-tailed test. This is the greater than symbol. This is greater than has increased. This value that we use, these two things right here, are always going to be the same number. These proportions are always going to be the same number. This is the number we are assuming is true until we prove otherwise. So those will always be the same, and the null hypothesis will always say equals. Then we'll have the symbol on the alternative hypothesis. It's kind of a little bit of a review from Thursday. Okay. This says for you to select this level of significance based on the seriousness of making a type 1 error. Basically, this means how badly will this thing be messed up if I reject the null hypothesis? Is it going to be really bad if I reject the null hypothesis when I shouldn't? Is that going to be terrible? That's how you determine what level of significance you're going to use, your alpha. But you don't have to choose your alpha. It will be chosen for you every single time. So don't worry about that unless you're doing your own study and then you're going to choose your alpha. Basically, if I do this wrong, if I reject the null hypothesis when I shouldn't, is it going to cause significant issues with whatever it is I'm working on? So we want to make sure that we're making good choices. Okay. When we're doing the classical approach, we need a test statistic. All the test statistic is that z-score. I'm going to write this down. Z-score, that is a highlighter. It's the z-score based on our sample. That's what the test statistic is. This right here is the new standard deviation. STD-DEV. That's the new standard deviation. We take our p hat, which is from our sample, subtract the given mean from our hypothesis, our null hypothesis, divide by the standard deviation. Notice with the new standard deviation, we are using the null hypothesis. It is because we are assuming it is true until we prove it isn't. So use the null hypothesis until we show it is not true. So that's the test statistic. That is what we're going to compare to the critical value. Yes, new standard deviation and standard error are the same thing. And a lot of times they just refer to it as the standard deviation. And so that's why I threw new on it. Standard error and new standard deviation, identical. Good question. Thank you. Okay. Now, the difference with our confidence intervals. So the confidence interval that we're used to based on chapter 9 is two-tailed. So we take our alpha and we divide it in half. So that's how we'd find those critical values. This area out here is the critical region because if or here, all of this, these right here are the critical region because what that's telling me is if my sample lands me out there in the critical region, it's going to cause me to reject the null hypothesis. So if my sample lands me out there, that's kind of a critical thing. I'm going to reject the null hypothesis. The critical value. So our critical value, we're dividing our alpha by 2 on a two-tailed test. Your critical value is going to be negative on a left-tailed test every single time, and it's going to be positive on a right-tailed test every single time. So we don't divide the alpha in half for a left-tailed or a right-tailed, only for two-tailed. I'm going to say it again. Don't divide your alpha in half on a left-tailed or a right-tailed, only a two-tailed. All right. I know this is a whole lot of stuff. It's not super complicated once we get into it. I'm going to step you through it, like baby steps through it. Okay. So on a two-tailed test, I've kind of already mentioned this. If I already kind of mentioned this, but on a two-tailed test, if our test statistic lands us out there in the critical region, we reject the null hypothesis on either side, above or below. Left-tailed, if it lands down there in the bottom below our critical value, reject the null hypothesis. Right-tailed, if it lands over there above our critical value, reject the null hypothesis. That's all this stuff right here is saying. It's just putting it in terms of Z. It's a nice little table, but it's a lot of words. Okay. P-value approach. We generally allow our calculator to calculate the p-value. We don't usually do this by hand. We don't usually do this using the z-table. Even though our notes say you can use the z-table, which technically you can, we generally just do the p-value with our calculator. So I'm just going to tell you that's what we're going to do with the p-value. Okay, I'm going to keep going. All right, this is the important piece right here. Once we find our p-value, this right here is your gold. If your p-value is less than alpha, reject the null hypothesis. Say it again. If your p-value is less than alpha, reject the null hypothesis. If your p-value is greater than alpha, fail to reject the null hypothesis because the p-value is the probability of getting that value in your sample if the hypothesis was true. Okay. let's actually do some math here. I'm going to do both. I'm going to start with just the classical approach, comparing test statistic with our critical value. And then once we do the calculator functions, then I'm going to show you the p-value approach. Okay. 1997, 46% of Americans said they did not trust the media when it comes to reporting fully and accurately. 2007, 1,010 adults nationwide, 525 of them said they did not trust the media. So we're going to use this level of significance. Just a second here, I'm going to highlight it. My alpha, 0.05. This is what we're using. This 46% is going to be my null hypothesis. Let's calculate. Actually, we're going to start from the beginning. So these are the things you're going to do on your test. First thing, does it tell me random? We're assuming random. Okay, the second here. Assuming random. It does not say we're going to assume random. Okay, second, because it's easier, I'm going to do the whole 5% of the population. So 1,010 is less than 5% of my population, because 1,010 is definitely less than 5% of all Americans. Next, NP times 1 minus P. So my N, 0.46. So, sorry, my N is 1010. P is 0.46. Remember, we use the hypothesis, the null hypothesis, until we prove it wrong. 1 minus 0.46. Let me check a look. Uh-oh. Times 0.46 times 1 minus 0.46. I got 250. That is greater than or equal to 10. Okay, so I tested, is it random? Is it independent? Is it normal? I tested all of those things. Those things need to be tested on when you're doing your test. Put those first. There will be some questions that don't require you to do top to bottom. It will say on the question, show every step of your hypothesis testing in your notes. So those two questions, I want to see all of it. There are some smaller questions that are looking for just bits and pieces. You don't have to show everything on those. Only the ones that tell you to show every single step. All right. Now we need to calculate p hat. So my p hat is 525 divided by 1,010. Okay, I have 0. I'm going to do 0.52 because it's 0.5198. So 0.52. That's what I'm going to use. All right. Before I do anything else, now I'm going to say, I probably could have done this before my p hat. Oh, darn it. Stop it. I could have done this before my p hat, but it's just where the wind took me. I have to write my hypothesis test. So my null hypothesis is that p equals 0.46. Your null hypothesis will always have an equal. So it's saying, I think the proportion of Americans who don't trust the media is 46%. That's what the null hypothesis is. That's what the studies have shown. My alternative hypothesis is going to be what does it say? It has increased. These are the words. They think it has increased. Okay, so that means it's going to be a right-tailed test because it has increased. So I'm going to say we think it's greater than 0.46. We think it's greater than. That is my alternative, my null and my alternative. I'm going to move these up to the top. Don't get motion sickness. Just because I want them out of the way, I'm moving those up to the top. So along with my p hat, I want the mu sub p hat. and that is the 0.46. We use for our mean, we just used what the null hypothesis is, the 46%. All right, this is lovely, lovely stuff. I'm going to write down that my alpha is 0.05 just because I like to keep everything in the same place. All right. Before I calculate my before I calculate my test statistic and so my and my standard deviation and all that jazz, before I do that, what I'm going to do is I'm going to get my critical value. So that would be Z sub alpha. I know that there's a lot here. I know this is a lot of steps, but this is kind of like our grand finale. So it is what it is. It definitely will not be, I think the homeworks are a little bit shorter or they just want bits and pieces. I'm going to pop over to my Z table. Maybe if I can find my Z table. There it is. Take a look at the bottom of your Z table. Hypothesis testing, critical values. This has the most common ones. These are the most common critical values. I love that they separate them left-tailed, right-tailed, two-tailed. So right-tailed will always be positive. Left-tailed will always be negative. Two-tailed, you're using both the positive and the negative. So right-tailed, always positive. Left-tailed, always negative. Two tails, both the positive and the negative. We're looking at 0.05 of our significant level, and we have a right-tailed test. So my critical value is 1.645. If it is a value that's not here, you can use inverse norm, but be careful because if you use inverse norm for a two-tailed test, you need to cut your alpha in half. So two-tailed test, cut the alpha in half. Otherwise, you can just use inverse norm with that number. Okay, let's go back. Okay, I know this is a lot so far. Let me before I finish this up, any questions on any of the stuff I've done so far before I do more here? I know this is a lot. All right, let's calculate our test statistic. I'm going to rewrite what it is. Different color. Let's do purple. Purple's pretty. Okay, so our test statistic. Test statistic. I don't remember what they do with it. What did they call it? Z sub zero? Okay, which is Z sub zero. I couldn't remember what they did. That when it's sub zero, it's pronounced not, so it's Z naught. It's going to be P hat minus P divided by the square root of P times 1 minus P over N. I usually do the standard deviation by itself and divide it just because it's a lot of places to make mistakes. So let's do that first. So my standard deviation sub p hat is going to be 0.46. Remember, we're using the null hypothesis, 1 minus 0.46 divided by n. Doing it independently just kind of helps a little bit. Make sure if you do it independently, you round a couple of decimal places farther than you need it. So square root 0.46. Well, I need a parenthesis. Parenthesis around the numerator, 0.46. 4 divided by. Nobody called me on that I didn't write 1010 down here. It's all right. So I'm going to go a few decimal places out. 0.1568. That's how far I'm going to go out. All right. Let's calculate that test statistic. Pink is good. Let's go with pink. Okay, so I have Z naught equals my P hat 0.52 minus the P given 0.46 divided by 0.01568. Remember, if you put this whole thing in the calculator, you want to put parentheses around your numerator. There will be a calculator function coming soon. Okay, it's approximately 3.83. Wow, that is huge. That is a huge test statistic. All right, let me show you what we have just found. Because this is a lot of stuff on this page. I know it's super busy. I'm going to draw, because I can, draw a picture. So here's my normal curve. I'm just going to put it right here in the middle. Here's my normal curve. My critical value, the critical value is this right here. Critical value puts me 1.645 standard deviations above the mean. So my critical value is right here, 1.645. My test statistic, the test statistic is this right here, which is based on my data, puts me way out here, 3.83. My test statistic is outside of this right here is my confidence interval. This is my confidence interval. My test statistic puts me in that critical region outside of the confidence interval. Therefore, I'm going to reject the null hypothesis. So I'm going to see if I can fit this in here. Okay, I think I'm going to put a square and then just kind of write in it so I'm not messing anything up. When you write your conclusion, make sure that you reference why you reject the null hypothesis. So out in the world, you don't have to tell me why, but you're justifying your reasoning for me. You're justifying this. So you would say, since my test statistic is greater than the critical value, we have sufficient evidence. I'm writing really small, sorry. Evidence to conclude the I'm just going to say those because I don't have enough room. Conclude that those who don't trust the media is greater than 46%. Therefore, we reject the null hypothesis. Okay. I know that's like really small and a lot. So what I want to see in your conclusion, why did you reject or fail to reject? So what in your math showed you that you should reject or fail to reject? And then I want to see the words, we reject the null hypothesis, or fail to reject the null hypothesis, or we do not reject the null hypothesis. Make it really clear whether or not you rejected the null hypothesis and why you did it. Make those two things very clear. I need to see that you understand. Okay, before I go through the typed things of exactly what we just did, are there questions about what's going on here? Okay, I'm going to pop over. We're going to go through the typed stuff. I know I've already done it all, but it's just, that's my MO. Okay, so this is all the stuff that you are checking. This is the stuff you are checking. I love the way that they set it up. So if my page is really messy, looking at their setup is a really good idea because theirs is not really messy. So this is beautiful. I love that it shows that the independence, it shows the normal, it shows simple random sample. It shows the setup of the null and the alternative hypothesis, shows your level of significance, gives you your p-hat, and then they calculated their test statistic. They do things slightly different order than mine, but that's okay. Next, what they did was they determined it was a right-tailed test. I don't care if you write down that it's a right-tailed test. Your null hypothesis shows me that you understand that. But they did find there's their critical value. Then this right here, I'm okay with words that simple. They write there's a lot more, but if your words are just that simple, 100% okay. But I need to see those two things. Test statistic is greater than the critical value, rejecting the null hypothesis. I need to see those two pieces in order for you to get full credit on this. Okay. So, um, I'm going to show you. Oh, so this is basically if I was going to use the Z table, or if you were going to use, just a second here. So I'm going to jump to my calculator. This is not what we're going to do, but I'm just going to kind of show you how you can calculate that probability. Remember a long, long time ago when we used normal CDF? So I want to know the probability of getting a Z score greater than 3.83. Remember the 1E99? This is not the way we're going to do it, but you can do it this way. Hit enter. So when you get something like this is kind of why I did this. This number right here, this is not 6.41. You can't have a probability that's 6.41. Notice this E negative 5 right here. This is scientific notation. So what this is saying is 6.41 times 10 to the negative fifth. I'm going to write this down on my iPad so you can kind of see what's happening. And I will go back over there in a second. Okay, I'm going to pop back over. Okay, okay. This right here is the same thing as saying 6.409 times 10 to the negative fifth power. So essentially what you need to do in order to put this into regular numbers, move the decimal place 5 places to the left. So what this is this right here. So I just moved the decimal point 5 places to the left. This number is so small that basically we're saying there's practically a 0% chance of getting a sample that looks like that if the actual percent was 46%. There's not quite a zero chance, but really, really low. This number right here is smaller than our alpha of 0.05. Therefore, we can reject the null hypothesis. This right here would be the wording that you can use for your conclusion if you are using p-values. This is the wording that you can use. The p-value is less than the level of significance, so we reject the null hypothesis. That's the words that you can use. That's very, very simple. Feel free to type that. So that would lead us to rejecting it. I can't tell you how many times I've gotten people that put the probability of 6.4. Now, obviously, a lot of people have not encountered the scientific notation, but just recognize that we can't have a probability greater than 1. So something's wrong. So at least question yourself on that. But that's what that means. Move the decimal 5 places to the left. All right. They write their big thing right here. Theirs looks a little bit different than mine, but I specifically want a little bit more than that on your conclusion. So they just here they don't say the words reject the null hypothesis. I want to see that. They also don't say why they rejected it, but that's because they don't have to. They're not taking a test. They're just, and they don't have to share all the rest of their findings. They're just saying there's the evidence there. I want to see that you understand what you're doing. Okay, I think the next screen. Okay, I don't know why I don't give you the calculator function. We're going to do this though. We're going to go back. So let's pop back to the page that has all of our information. Boy, this is a lot. Okay, I'm going to I'm going to erase this. Is everybody okay with that? It kind of makes me sad erasing it, but I need to erase it because I this is overwhelming. So we're going to make the eraser as big as possible, and I'm just going to erase it. I can't get my lasso around it. Oh, I can't get my lasso around it in order to just delete it all. But I'm going to at least give get enough room to write. Okay, our calculator function. I want to make sure that I write it correctly. Calculator function. 1 proportion z test. This is our calculator function. 1 prop z test. 1 prop z test. We're going to do this in the calculator. So I'm going to pop over there. Clear this out because I don't like a messy calculator. So you're going to go to stat, arrow over to tests, and it is on mine, it is number 5. I don't know where it is on yours, but it's number 5 on mine. It's 1 prop z test. Hit enter. P naught, that is your null hypothesis. It does not know what prior information you have. It is completely unaware. The other thing it does not know is the critical value. So if you're comparing with the critical value, that's something that you just write on your paper. Go down here. There are 525 that were our 525 were our successes. Our sample size was 1010. Now, this is the most confusing part. So notice that over here, the arrow is pointing to 0.46. On my greater than symbol, the arrow is pointing at 0.46. If it was less than, it isn't less than, but if it was P was less than 0.46, then the alligator is trying to eat the 0.46. So notice whether the alligator is eating the 0.46 or if the arrow is pointing at it. In this case, the arrow is pointing at it. Don't worry about colors. I'm going to go down to calculate. Now, if you are not doing all of the math on your test and you are using the calculator function, I want you to write down what you put on this screen. I want to see P naught, X, N, and your greater than P naught. I want to see this screen. Calculate. I want to see this screen. These are the 2 screens I want you to write down. So still do all of that beginning stuff, the NP1 minus P greater than or equal to 10, the less than 5% of the population. Show me your null and your alternative hypothesis, but then write down what are on the screen so I know what you put in your calculator. Okay, so it gives this z-score that it gives us is the test statistic. It calculates that for you. This P is your p-value that you compare with your alpha. This is the p-hat right there. And then this is your sample size. So all of that information is right here. You don't have to do all those other calculations. If you are comparing your test statistic with your critical value, you're going to need to write down the critical value. On the test, I do not care which method you use. If you're using the p-value method, just compare your p-value with your alpha and then give me your answer there. If you are comparing your critical value with your test statistic, then that's what you're going to do. Write down your critical value. You don't have to do both things. Just pick one. Pick the one you like best. I don't know why I like test statistics and critical values, but most people use p-values. It does not matter. But this gives you both test statistic and it gives you your p-value. Compare two things and give me your answer. Right. Go back over here. Questions. Because this is the end of 10.2. So now's the questions for proportions, and we're going to jump to means. All righty then. Popping over to, that was the end. 10.3 is a little bit, it's not a ton different, but it's enough different that, I mean, it's all the same stuff with our left-tailed, right-tailed, two-tailed. We are going to be using t-values again. And our n-1 degrees of freedom, we're doing that again. And that's for our critical values. Our test statistic, the same thing. So this right here is our T naught is going to be your mean from your sample minus the mean from your hypothesis test, your null hypothesis, divided by the standard deviation. Now, all we're going to have is a sample. So for our standard deviation here is going to be based on the sample and the sample size because we don't have a population standard deviation. So our new standard deviation, standard error, standard deviation, standard deviation. Okay, either one. Those are the same thing. New. I'm going to put new here. Those are the same thing. Standard error, new standard deviation. Sample standard deviation based on your sample divided by the square root of your sample size. Not n-1. Use n. Okay. Just remember that our t distribution is different for degrees of freedom. All of this other stuff is just all the t values, but the t values require or depend on your sample size. That's the important thing there. T values depend on your sample size. Okay. We don't need all that. All right. So these are the things you test. I am okay if our sample size is less than 30 and it doesn't state that that the population is normally distributed, you're going to assume it's normal. But you're going to have to write that you are assuming normal. You're also going to have to write that you're assuming random sampling if it doesn't say. These things you have to check. Notice that with a mean, we don't do NP 1 minus P greater than or equal to 10. It doesn't even make sense. So remember the rules regarding if it's normally distributed. Either the population is normally distributed or the sample is greater than or equal to 30. Those are the things that you got to check. Sample values are independent. That is our sample size is less than 5% of the population. So these are the things you're going to test. On the big problem, on the test, when it says show every single step, you're going to show this. This is some of your points. These points are worth this. These problems are worth 10 points because you're going to show every single step. All right. Now, the only difference with the hypothesis tests here is we're using mu instead of p. Everything else is the same as with the p, except for we're using mu instead of p because mean. And we're using mu because we're talking about our population until we show that it's not possible. Our population mean is this until we show it's not possible. Right. Okay. So here's how we do this. They'll give you a level of significance. We're going to give that to you. Compute your test statistic. Your critical value is going to be this. So our critical value is going to use the n-1 degrees of freedom. Our test statistic does not. Our test statistic uses the actual sample size. Critical value uses n minus 1 degrees of freedom. I'm going to write these words down. Test statistic, use actual sample size, critical value, n minus 1 degrees of freedom. There we go. Bam. So very important. Otherwise, you're going to get the wrong numbers. Give you a second to write that down. Then we will continue. Okay. This is exactly the same thing. We're going to have our critical values. If your test statistic lands in that critical region, then you will reject the null hypothesis. If it lands within your confidence interval, then you fail to reject the null hypothesis. Okay. Then you can p-values. Now, we basically do not use the table. It says to use table 6 to approximate your p-values. We pretty much don't do that. So just don't do it. Don't do it. And we don't have a special calculator function to get p-values except for the test that we're going to use. We don't use like normal CDF is what I mean. There's no like normal CDF. It is, you'll see. I'll show you. We'll get there. All right. Okay. If the p is, I didn't tell you guys this yet, but I'm going to tell you anyway. So when I was teaching AP stats at the high school, they kept forgetting about whether um, the p-value was supposed to be less than or greater than the alpha. So because I'm silly, if the p is low, reject the hoe. There you go. There's the way that I got my high schoolers to remember it. See, I got a chuckle out of you. So if that helps you, if the p is low, reject the hoe, use it. If the p value is lower than your alpha, reject the null hypothesis. This is how you get high school students to remember things. Hey, it could be how you get college students to remember things. So if it helps, use it. I know, I'm silly, but you guys already knew that. You've known me for a while now. You know I'm kind of goofball. All right. So is my cat. She's not being helpful. All right. We all got this. The p-value is less than alpha, reject the null hypothesis, then you state your conclusion. See, I've got a laughter in the chat. Please don't report me. I don't want to lose my job. I don't think I'd lose my job, but you know. All right. Okay. Now, as this says, this procedure is robust. Minor departures from normality will not adversely affect the results. Um, we don't use this if we have small samples with large outliers. Don't worry about it because any sample I give you, we're just going to assume and you're just going to do the math with. Um, Now, if you were using your own data, let's say you were collecting data and you wanted to do this whole null hypothesis thing. In fact, I'm going to be doing it with uh, smelling ants thing because we did talking to more students today and all of them, all but one of them could smell ants. So I'm actually going to do a hypothesis test with ant smelling. I need to get more sample and I'm going to actually probably put it in my PowerPoints for next term because I'm just dying to know. Dying to know. Anyway, so as long as it is normal, as long as you're kind of normal, so if as long as there's not huge outliers or things, it's fine. But any data that I give you is going to be just fine. So just use it. Okay, let's do this one. Okay, assume the resting metabolic rate of healthy males in complete silence is 55,710 kilojoules a day. Researchers measured the RMR of 45 healthy males who were listening to calm classical music. They found their average, this is my mu, to be that with a standard deviation of that. Our level of significance is going to be 0.05. We want to know, is there evidence to conclude that the RMR of males listening to calm classical music is different than 5710 kilojoules a day? That word different tells you it's two-tailed. All right, let's do all our stuff. Sometimes I just like to number them. So 1, does it say normal? No, but we have a large enough sample size. So our sample size is greater than or equal to 30. So we're going to check normal. Because our sample size is greater than 30, we're good on normal. Next, number 2. 2, it does not say. So we're going to assume random. We're assuming random. Okay. And they measured 45 healthy males. And so 45 is less than 5% of the population. So we're good there. I'm going to put check marks everywhere because check marks make me happy. Okay. Because it makes me feel like I'm checking off a list. So those are 3 things you need to check. You can check them just as simply as this. I'm cool with this for your checking, but you need to check those things. Next, I'm going to write my null and my alternative hypothesis. So my null hypothesis, I'm putting it up top because it fits well there. Mu is equal to 5710 kilojoules. Okay. So mu is equal to 5710 kilojoules. Alternative hypothesis. Mu is not equal to 5710. Remember that that number is always the same, only the symbol in between it changes. Since it says different, this is not equal to. Okay, this is lovely. I'm going to write a few things down. My mean, woo, that's weird. My mu sub x bar is 5708.07. My standard deviation sub x bar, no, this is just a standard deviation. S, not sub x bar yet. 992.05, because this is not my standard error. This is just a standard deviation of my sample. All right. I'm going to go get my critical value. So remember, critical value is based on 1 minus it's my n minus 1. So my n is 45, so I'm going to use 44. Now our alpha is 0.05, but this is a two-tailed test. So I'm going to use alpha divided by 2. So 0.05 divided by 2, that is 0.025. That is what we're going to look at on our table because it's a two-tailed test. It's the only time that we cut it in half. So I'm going to have my t sub alpha divided by 2. We're going to go look at this. 45 is my sample size. We're going to use 44 and 0.025. All right. There we go. Okay. So my 0.025 is right here. Notice when I scroll down though, when I get down to 45-ish, it jumps straight from 40 to 50. So it is such a small difference. I usually just find the halfway point or about the halfway point. So using 44, I could just use 2.010 if I wanted to, or 2.015, or remember our fancy schmancies? Let's do, now I know that all of you have oops, sorry, clear. Not all of you have the inverse t. Remember, we can do this. So I could do 0.025. Degrees of freedom is 44. So I said what, about 2.015? See how close it is. 2.015. So I'm going to use plus and minus because we both positive and negative, 2.015. So when you put your alpha in your inverse t, you are always going to get a negative, or when you put your alpha into inverse norm on your regular calculator, you're always going to get a negative, but you just need to know two-tailed tests, we use both. Left-tailed, we use negative. Right-tailed, we use positive. All right, pop back over. Okay. Uh-oh. Go up there. Okay, so I've got this is my critical value. I'm going to write it in another color really small. Critical value. This is your critical value. Okay, that's good. It's all good stuff here. Let's talk about our test statistic. I want my test statistic. Test statistic. Remember that is our x bar minus mu divided by the s divided by square root of n. But as before, I like to calculate my standard deviation separate. Try to make a little bit of room here. So I'm going to do that over here. You don't have to. You could put the whole thing in your calculator at one time. I just fear my own typos. So my sigma sub x bar is going to be standard deviation 992.05 divided by the square root of 45. And I'm going to round a little bit farther than, I'm in a weird spot on my calculator. So it's 147.886. I'll go that far. So that's my standard deviation. So now I can calculate my test statistic with that number. So let's do that. So T sub 0 equals 5708.07 minus 5710. If you put the whole thing in your calculator at once, parentheses around the numerator, 147.886. 07 minus, close my parentheses, divided by negative 0.0198. Okay. This is my test statistic. Highlight that. Over here is my critical value. I'm going to highlight that also. I'm going to use my little drawing. Hey, that's a highlighter. Okay. Okay. My test statistic, my critical value, 2.015 negative and 2.015 positive. This right here, this test statistic puts me barely below the mean, right inside there. It is smack dab in the middle, barely below the mean. I don't know where I'm going to write my conclusion, but I'm going to write it in a second. So my test statistic lands me in the middle of the confidence interval. Therefore, I'm going to fail to reject the null hypothesis because it is not beyond, it is not outside of my critical values. Therefore, I'm going to fail to reject the null hypothesis. I'm going to find some room. I'm going to erase that because I think I'm going to do it on the side up there. I think that that's probably where I have the most room. So I'm going to make a square over here. Okay. Okay, since the test statistic is, I'm going to say between the two critical values. I like that. Between the two critical values, there is not sufficient evidence that's word is going to put me off the edge, that the mean RMR of males. I'm not going to put listening to music because it just takes up too much room, is different than 5710 kilojoules day, uh, day. Therefore, we fail to reject the null hypothesis. Bam. Give you a moment. That was a lot. Questions on this before we move on? We're almost done. I know it shows 44 out of 57. Trust me, we're almost done. You guys are troopers. Fantastic. All right. I'm going to pop over to the other screen. So once again, um, this is showing the thing. Sample size is large. Um, it doesn't give did it give the independence? This one does not give all the stuff. It just says sample size is large, we're following it. It doesn't do the independence and all that, but you need to do that. So we have our null and alternative hypothesis. It shows the level of significance, shows our sample mean and standard deviation. It calculates the t-value, the test statistic like we did. This one shows it's a two-tailed test. It finds our critical values, and it says the same thing. These words are good. I'm not going to be super picky about using context. Now, if it says use context, then use context. If it doesn't, then as long as you're specific about why you rejected or didn't reject and whether or not you rejected, be really specific about those two things. Make sure it's very clear. I want the word reject in there. Do not reject, reject, fail to reject, whatever. The word reject needs to be in there. You need to tell me why you chose what you did. Okay, as this says, by hand is not exact. We're going to use something called t-test. So I'm going to jump to the calculator. Maybe that's the other direction. All right, let's jump to the calculator. Go to stat, over to tests, and it's called t-test. It's number 2 on mine. So stat, tests, t-test. This is similar to calculating confidence intervals. You can either put data into your list 1 or you can put stats. We have stats on this one. I need to go back because I don't remember my numbers because apparently I have that kind of in mind. Okay, my mean is 5710. That is my null hypothesis. It has the little knot next to it because this is gonna, and now we have our X bar. It gives us the X bar, 5708.07, and it gives me a standard deviation. This is the actual sample standard deviation, not the sub X bar one. So it gives us, where is that, 992.05. This one's easy because it's not equal to, okay, this is 45. This one is easy because it's not equal to. Just pay attention to whether the null hypothesis, the number, is being eaten or pointed at, or not equal to. This one's pretty easy. Go down to calculate and hit enter. The reason our p-value is so high is because our test statistic is super close to the mean. This is the same number that we got. It is super close to the mean, so our p-value is humongous. Most of our p-values are not going to be that big. But that number right there is clearly larger than our alpha. So you could say, because the p-value is greater than alpha, we fail to reject the null hypothesis. This gives you your X bar, your standard deviation, your sample size, because it's all the information. Once again, show me what's on the screens. Now, if you're using it with the data, so let's say that now this data is, whatever data I have in here is not going to be appropriate, but I'm just going to do this. So if you're doing it with data like this, you don't have to show me this screen because this screen is kind of useless, but definitely show me the other screen. I want to see your output. Give me this screen right here, the whole screen. Now, obviously, you don't have to go out however many decimal places this is. Just go out like 3 or 4. Same thing with the test statistic. Just go out a few. But I want to see what popped up on your screen. Tell me you used t-test, and then show me what popped up on your screen. That's going to be part of your 10 points. Give me all that stuff. So test statistic is in between the two critical values, where the p-value is greater than alpha, either one of those. Right. Questions, comments, queries, concerns? Where is it? Okay. I just went back to this so I can get my stuff. We have one more that has data. And we're not going to go through everything. Basically, what I'm going to do is I'm going to show you what I want from you if you use your calculator. That way, there's no questions. Okay. Go through all these extras. All right. According to the United States Mint, quarters weigh 5.67 grams. A researcher is interested in determining whether the state quarters have a weight that's different from the 5.67 grams. He randomly, it's a great word, look at that, randomly selects 18 state quarters, weighs them, and obtains the following data. Okay, the first thing we're going to do, yes, random sample. I'm going to put a check mark because check marks make me happy. All right, next, we are going to, because our sample size is less than 30, we're going to assume normal. Let's see here, 3, 6, 9, 12, 15, 18, yep. Okay, assume normal. Okay, and my sample, 18, is less than 0.05 of the population, so we're independent. Bam, do that. I want to see these things. Do that. Next, my null hypothesis says that the mean is equal to 5.67. My alternative hypothesis says that the mean is not equal to 5.67. Show me that. The other thing we can't get from our calculator is our critical value. Z sub alpha up t. T sub alpha divided by 2. Let's look that up. So once again, alpha is 0.05. 0.05. So this means alpha divided by 2, 0.025. Not a bad idea to put there. I'm not going to mark you down for not having that there, but putting that there kind of just triggers your brain for what you're looking for, because we're also going to use n minus 1 is going to be 17. So let's go to our table. Okay, let's go. Where's my thing? 0.025 is this column right here. Now scroll down. We're using 17. So our critical value is 2.110. Can I do this? Yeah. Critical value is 2.110. You don't need to, don't do that. Okay. Because I use 17 degrees of freedom because it's n minus 1 and the 0.025. That is my critical value. That's what I wrote down. All right. So this is my work so far. All of the housekeeping stuff that we need to do before we can do any math. Now we need to put this in our calculator. Go back over here. Go to my list. Kind of wish I'd have done this ahead of time, but it's okay. You all need time to put it in your calculator too. 0.7. I just did something weird. Okay, 5.62. Point 0.73. Okay, I'm going to give you a second to catch up. Unless you have already. All right, are we all caught up? Okay, once again, click on Stat, go over to T-Test. I want data. Okay, the mu naught right here, we have to type that in because it doesn't know what our null hypothesis is. It does not know. So you have to type that in. Type in the null hypothesis. It needs to be list 1 because that's where we just put it. Frequency, just leave that as 1 and not equal because we're at different. So don't forget to type in the null hypothesis up here at mean. Otherwise, you're going to be basing it off some random weird number. So make sure that's there. Okay, I'm going to go down to calculate and hit enter. And I'm going to write this on my screen because I want to show you what I want from you. Okay. T equals 2.75. P equals. Okay. Okay, I wrote all that down. I'm going to show you what it looks like. The T here is the test statistic. Yes. So the question, it says double checking what the T here is again. Yes, it is the test statistic. So this is what we're comparing to the critical value. Yes, perfect. Okay, let me go back to my iPad. So this is what I wrote. This is what I want you to write. If you are using your calculator and not hand calculating it, not using the formulas, this is what I want you to write. All of the stuff I have on the screen is things I would love to see in your work. Now, on the test, it's going to say to type your conclusion in the box. So all of this stuff is going to be on your paper, on your work. And then it's going to say to type your conclusion in the box. That's where you're going to say the stuff that I'm going to say right now. You're typing it in the box. Kind of like remember with the box plot on test one, I just had you type done, but this you're going to actually type out your conclusion. All right. So I'm going to create a box here that I think because I've been writing one based on test statistic and critical value, I think I'm going to write one based on alpha. I haven't done that one yet. Even though you can see your test statistic is greater than your critical value, right? You can see that. And one thing I didn't do, you can you can sue me later. I didn't put plus or minus on my critical value. I probably won't mark you down on that, but plus or minus is important. Okay. So I'm going to say since the p-value is smaller than alpha, okay, alpha equals, or you can write alpha since you're going to be typing it, alpha equals 0.05. There is sufficient evidence to suggest the mean weight of state quarters I'm running out of room is different than 5.67 ounces. Ounces, grams. Grams, grams. Therefore, we reject the null hypothesis. I'm out of room, so I'm not spelling that word out. So that's what you would type in the box. Since the p-value is smaller than alpha equals 0.05, even if you just said p-value is smaller than alpha, I just like to put that 0.05 in there. You don't have to put that in there. Just say the p is smaller than alpha. There's sufficient evidence to suggest the mean weight of state quarters is different than 5.67 grams. Therefore, we reject the null hypothesis. Right. Questions here? I feel like this doesn't take us, this is just kind of taking our confidence intervals to the next level. It's just applying it in a different way. I love that we're using all of the same stuff and just adding a little bit, making it a little more nuanced, maybe, just adding another layer to it. 8, 9, and 10, in my opinion, are the three chapters that go best together. So at least when you're taking your test, they all kind of go pretty well together. And it's going to be pretty clear when I say build a confidence interval or or show that it is different now. I feel like the wording is going to be fairly clear. I think the screens at the end, I think the wording I'm going to be working on again. All right. So once again, the now this suggests that we actually find if there are outliers. I'm not going to make you do that. So if you were doing this in your own grand experiment, you would want to test that there's no outliers in your data. I am not going to make you do that. You're going to just assume normal. If this was your own experiment and you were using sample sizes less than 30, which just don't do it, then you should test for outliers. You know how to do that with your two standard deviations. You know how to do that, but we're not going to do that because I don't feel that it's necessary because I'm giving you the data. All right. This is just showing that that's normal. this is the same stuff that we did. We have our hypothesis test, we have our level of significance. They calculated the mean and all of that. There's our test statistic. It's the same thing that we got. And using n-1 degrees of freedom for your critical value, don't forget that. Don't forget the n-1 degrees of freedom. Don't forget that. They compared the test statistic with their critical value. They rejected the null. And then they have their p-value. The p-value is less than the level of significance. We reject the null hypothesis. And there's sufficient evidence. I guess it doesn't show at the end, but I'm going to show you a resource you guys do have. All right. Go back to Blackboard. That was the last of our slides. That is the last slide for the whole term. How crazy is that? You know you guys are going to miss me. You may not miss my math, but you'll miss my quirkiness. You're going to go on a Zoom on next term and be like, man, this guy's dry. Okay, let me go and show you a resource you have. Oh, that's so sweet. Okay, going down to week 9 and 10 here. I'm getting ready for test 3. I highly recommend you print this off. Final review PowerPoint right here. I highly recommend you print this off if I can get it to come up. If not, then I will absolutely fix it. Okay, there it is. All right. On the first page, it gives you basically everything you need for confidence intervals. It tells you critical values. So this is confidence intervals for mean, confidence intervals for proportion. And it gives you all of the stuff right here for your confidence intervals. And does it have I don't think it has it doesn't. Go back. Okay, the one thing, oh, it does have it right here. Tells you how to calculate your what the sample size needs to be. So that's right there. It tells you the calculator function. Once again, sample size, calculator function, all of that is right here. Then the next page is hypothesis testing. It does all the same stuff. Don't use binom PDF for your p-value. So take that off, because yes, you can, but don't. Just don't. So it's on a timer or something. So don't do the binom PDF for your p-value, but all the rest of the stuff, do it. This is like super helpful here. Even reminds you the n-1 degrees of freedom. Now it doesn't tell you every single little piece that you're going to need for your test, but I gave you that. I showed you start to finish what I want to see on your test. So do that. It's all right there. All right. So any questions while we are on recording? All right, let me turn the recording off if I can find it. Okay, stop recording.